Hi and welcome to the basic tutorial of Vision. Let's start with how to download Vision. Therefore you go to our GitHub repository where you can find all new things, the user guide as well, and our releases. Currently we are on the release 1.02 where we freshly added the live file format and did various things with the channels. You can see the general information of the changes here and also the bug fixes. But here down below, here are the assets. Here you can download your version that you want to have. First here the Mac version, the second the Python where everything essentially is in place, and the Windows version. We are running it on Windows, so we are downloading it for Windows. Save it and wait until it's downloaded. Once the download has finished, extract it, or wait until it's done. And now you can copy this folder wherever you want it to have, because here it's the standalone version inside. Double click on the Vision, then the splash screen only on Windows will appear, and the console will open as well. Wait until it's done, and now Vision is ready to go. Okay. Now we will start with the basic menu buttons and what they are doing. Basically, the buttons are doing what they are saying. With this, you have load file. You can use the test image folder, which comes with every version that you download, and with load files, you can load essentially as many files as you want, or just 3 of them, and now the files are loaded in. Now you can do something with that. The load folder is basically also what it's saying. It's basically loading every file that is supported. Currently it's LSM, live, CZI, and omitiv in this folder that you have chosen, and loads it into Vision. If you want to clear this selection, that because you selected something, you have to press this button up here. If you want to delete one image because you loaded just one image that you didn't want, then you can delete this entry, just this one. You can also mark several and delete the entries that are marked, or just delete the whole table, and then everything is resetted. Next on the menu is how to use this panel here, and what's on the right side, and how to get a basic mask. For that I have chosen a test image from the folder. It's the 22 channel spheres, which are essentially lipid spheres, are bead supported bilayers labeled with NIRAD 12S dye. That's why we have here a nice spectral image here, and it is only one dimension. We call it one dimension. We have 22 channels, but no Z and no T dimension in this image. So, but basically what we want to do is we want to calculate the general polarization. Therefore, we use this equation. In this equation, we will dig in deeper in a different tutorial, but basically you can write here in this equation whatever you want. If you just want to subtract channel A minus B, you can do this, but for now we are using the general polarization equation. The A and the B is referring, maybe you've seen it already, to this A, to this B, to this C, to this D. If you would write here, multiply this whole thing with D, but you've chosen only channels for 655, 655, only for A and B, and you would press now test mask, which should result in a mask here, you will end up with an error message which is stating that you're using in the equation a different letter, D, but you have not entered anything here. So basically, what you can do is in the equation, you can use A, B, C, and D, and you have to use it afterwards here. Let's talk about how to get a better mask, or let's say it differently, what is this panel here below. So first of all, you can choose if you tick the specific channel, which channel you want to use as masking. So for instance, if you want to use the 512 channel, which is this one, you can tick it here, then you can use it as a masking tool. It's not that good, but what you can also do is you can go here, search for very bright and nice image. This looks quite good. So 610, tick this and do the masking again. Now we have a very nice mask. You saw that I ticked the 512 and the 601. You can tick as many as you want. What it does, it will use more and more channels for the masking, and you will get a better and better signal. It depends on your masking strategy, what you want to do, but basically you can use every channel to sum up and then use this new image as masking. Okay, let's have a look onto the thresholding modes, signal to noise ratio, background compensation, background mean, and so on. So maybe let's start with the background compensation, the signal to noise, and this. Signal to noise essentially refers to how much bigger must be the signal, our signal to our noise signal. You zoom in here, and you use the probe raw image. You do this, and then you can see here what's the mean, what's the median, standard deviation, minimum, maximum of your background. We can do this here as well. Okay, we have a mean value in our signal of 13. That's good. Our standard signal to noise ratio is set to 3. That's a good estimation. You can set this higher or lower. What it does when the signal is lower than this to your background is then it is not counted as a true in our mask signal, and so on. That's how it works. When you want to use the background compensation mechanism, then you do this. Maybe let's go back to the full image. I want to probe a bigger area, like this maybe, or maybe like here, and that's should only be the background. So I'm probing here. That's a very good image. I have a very low background signal. I have a very low standard deviation. And what it does, it automatically fills in background mean and the standard deviation. So now you can use the background compensation. We try to mask it again, and it didn't really change because our signal is very good. So this is helpful if you have signal to noise ratio is not that good. You can compensate, or you can try to compensate it with that function. What you also can do, because we are constantly using here the Otso automatic algorithm, so it chooses the thresholding point automatically according to the Otso algorithm. What you also can do, you can choose your thresholding value manually. So currently it's at 8. Let's see what it does when we test the mask again. You see our threshold is much lower than the Otsu was because our mask got increased. So if I would write here, I don't know, 10, maybe it's better, good, maybe 20, and so on. You can see we lose more and more of our mask because we increase here the signal. Good. Okay, let's have a look on the right side, the masking options, because there we have essentially our mask, but we can improve the masking, what it does. So What I want to show you is essentially the first part, or one of the first things, fill holes. I want to show you that? I want to show you that you can see we have some little holes in our mask because we are interested in the membrane of this bead, of this lipid bilayer. So we want to close this, and we fill holes with a small value. That's more or less trial and error because it depends on your image, on your pixel size of your image and so on. But for instance here, if I rerun the masking again, you will see these small dots are gone now. What we can also do, it's maybe not that important for now, but if I increase that very, very high, then I will fill holes in a bigger size. So what this means, the smaller the value here, the smaller the holes that you fill, the bigger the value, the bigger the holes that you're filling. Good. Let's redo this again. So the next point what I want to show you is the filter. We have here several filters: the Gaussian, the mode, the median, mean, geometrical mean, majority, minimum, maximum, sum, gradient, entropy. Many filter types. I want to show you one basic filter, the Gaussian filter, where you can use this value to increase the Gaussian size, the filtering size, or the filtering intensity. But what it does essentially, when I play this, you can see the membrane is much more smoother now, and I don't say better because this depends what you want to see, but at least the spheres are now continuous. Good, which you need for certain instances. What you can also do if you want to now dilate your mask, you can do this by an octagon, a disc, or a square, which you choose the dimensions of the octagon, the disc, or the square. With these two dimensions. Essentially, if you increase it, it will be increased. The dilation will be increased. So let's test it with the dilation and the Gaussian on. Now we have real big donuts. It's too high for our mask. We are now taking much more of our background than our membrane that we want. But just to show you what we can do here. Of course we can also remove some objects. If I do this now, keep dilation on, and we test this, you've seen here, maybe there was something. I'll show you again. This small bead that is just close to the image edge is now, if I remove the object, is now removed. And if I increase here the number, now these images, so now bigger objects got removed. So what this means, eventually everything gets removed if you increase this number to a too high number. So with 4 we got rid of this edged, of these half spheres and so on, which is good. The dilation is maybe a bit much. Okay, remove objects. So this, we can work with that. Okay, now we know how to create and how to manipulate the mask. We want to have the general polarization image, so we want to analyze something. We don't want to create only masks. So essentially, we have our mask, looks quite nice, we can work with that. All we need to do now is press the Run Analysis button. It runs it, and now we can see in the full image results, tap our analysis. Only the part in our mask data is analyzed, and now we got a calculated GP image with represents the beta value here. In a histogram, we have the intensities of all our channels in a histogram, and we get the phasor plot. These are just different representations that we want to give you to have a quick look. The full image results are, for me, a quick checkup. How does my image look? What do I have here? And so on. We also get some statistical values or some nice values to know. We have the median, the standard deviation. We know how many pixels are rejected. In our instance, in our image, no pixel got rejected because every pixel that would be in saturation, so in the maximum value of our bit depth, like 16 or 8-bit, this values got rejected because we don't know if you are already overshooted in the image or not. Right? And the mean intensity of the thresholding channel, it's 29. That's only nice to know parameters. Good. What we can do as well in this image, we can use the object detection. You can try this in every image, but essentially this image is quite nice. We just take the object detection part because currently in the object results there's nothing here because we have not analyzed it. We just tick it here and press run analysis again. Now it's taking a bit longer because now he checks the full image for single objects. And now you can see he found several objects. He tried to find only objects that are fully enclosed, such as this and that. He doesn't count as an object because we don't know what's happening on the edges, so only the full cells, or in our case beads, are detected. So now we can check the detailed information of the several objects. Sometimes it's a bit hard to detect, to define which part belongs to the other part, but this is a common problem. This is only really you can only get rid of these problems if your image allows that. So if you have, for instance, like the object 7, the bead 7, it's alone, then you can see the full image. But now you have here the overview of this single image, of this single object, the histogram, again the intensity, and the phasor plot of that. But here also we didn't have anything. This is when we choose the next point, the linearizer. With that we can create our next analysis step. It's the linearized profile. We have to run again the analysis. Now it's taking even longer. Maybe that's a good point to show you what's going on, and if you're analyzing a huge image, it will take longer and longer. So what's quite nice that we thought we implement or we keep here is in the console. Now when you run this with the objects detection and the linearizer on, or even without the linearizer, when you run it, you will see which objects has he detected and is actually the analysis still running. Sometimes it can happen if it's a very, very big image that the program can't analyze anymore, or he's still analyzing and you don't know what's going on. So when you press now this and you go in here, you see when he's done with one image or with one object, he reports, okay, number 27, it's done, and so on. And at the end, you also see it here, thread finished. That's always when he's finished, you get this message. Good. But back here, what we essentially did now with the linearizer, we go to our bead number 6 or number 7, doesn't really matter. What we did here, we linearized this membrane, this whole part, and have now the control over the full channel width to see what's going on in the membrane. So for instance, if you can remember, at 601 we had the best signal. So this here is the membrane, and when you go up, this is the inner part. We call it the cytosolic part because referred to the cells, it's the cytosolic. In here we don't really have a cytosolic part, but I can show you. The outside, there is nothing, and you can here see the membrane linearized. Good. What we can also do, we can profile the membrane. Let's see, have a look how many profiles we get. So we tick again here, membrane profile, and we run the analysis again. Should see here now Okay, we should see here now all the objects, and he's also telling you in which objects did he get a membrane, or actually in which object he does not get a membrane. So for instance, in object number 2, or he did not profile the membrane. So in image number 2, when we go to the membrane section, there is nothing, and also not in the profile. When we go into the section 1, then we get something. We see here the membrane zoom, you can see it here, and we can see that he detected now 3 different parts, no, not 3, 1, 2, 3, 4 different parts of the membrane. And down below in the membrane profile, here you can see the mean value of the profile. And here you can see that the blue part is here, the orange part next to it, the beige part is here, and the green part is here. So we color-coded essentially the parts of the membrane with the background here in the membrane profile. Good. And what you also can do, if for instance you have an image, like a spectral image or something else, and one channel you want to colocalize with your membrane part, you can do this by simply clicking on the colocalization and choosing which channel you want. Let's use the 601 and run the analysis again. Again, in the console you will see at which point you are and what's profiled. But now, if I have a look on to the membrane 1 again, where we had the membrane section, now you can see the red line. That's the colocalization. So here, apparently, we have in these different parts really a different signal. In this case, it doesn't really, it's just a showcase. So what you can do is you can colocalize your membrane signal, what you calculating, in our instance here the GP, with maybe a protein signal that you also have in a different channel. So good, so far. Okay, last thing on the analysis thing I want to show you is the cytosolic part, so the which we have here still empty. We're going back onto the left side. Because we can analyze not only the membrane, we can also analyze the cytosolic part. If you want to analyze the cytosolic part, you always have to analyze the membrane, because it works first with the membrane part and then it goes into the inner sections. But essentially what we are doing, it's completely similar to our membrane, as you can see. So we also have here equations. You can use here a different equation than in the membrane section, of course, but we keep it with the general polarization equation. So, and I also use the same channels here, 655. What I'm doing in here is I create now a fake cytosolic part. I'm using a Gaussian filter on my signal, and I dilate the signal to create a fake cytosolic measurement. I click here to cytosol measurement, and now I test the mask. Now you can see I got a mask in the cytosolic. So here you can switch now between the membrane mask and the cytosolic mask. If I increase, maybe let's use the fill holes in the cytosolic part. Now I got the inside, but it's fake. There is nothing inside. That's only noise. But if I do this now, and I do the object detection again, good, run this again, and now we should have in the object detection part also the cytosolic parts. We can switch here again between membrane and cytosol, and also here between membrane and cytosol. And of course, when you do this, you also see the cytosolic full image results also here. I'm going to show you a case of a, we call it 5-dimensional image, because we have the X, the Y, the channel information or the channel axis, and then the set and a time axis. So we have 5 dimensions, and you can also analyze these kind of images. For instance, here we have some GOVs measured in set from the bottom to the top of the GOV, and also in time. We have we see how some of the GOVs are moving around, and of course the general information, so the spectral information. So you can analyze these kind of images with we are using in this case again the general polarization equation. I'm using here Gaussian filter to create this mask. Let's try if it's working. Nice. We have still this very nice mask. Maybe we could tweak it a bit more, but for now, just to show you how this would look like, it's more than enough. And I show you here the object detection part. So we run the analysis again, wait until it's done. It takes a bit more because now we have not one image, we have at least 1, 2, 3, 4, 5, and this times 1, 2, 3, 4, 5. So 25 images that he has to analyze. But now he's finished. In the membrane we have again the full image results, and here we can move in the set axis, we can move in the time axis, and we see for each individual image the full image results. And of course in the object results we got also something, so we can have a look in here. The first object we have detected, or there was a small object that we could get rid of when we try to mask it a bit better, but maybe there is an information that is actually useful for us, I don't know. But here we have the third object and the fourth object, and again here we can switch through the Z stacks and the time stacks as well. So if there is something happening there, we can see it in the time, in the set, as for one object. That we can do for cytosolic measurements. We can linearize all the objects and so on and so forth. But keep in mind, you're not analyzing one image there, you are analyzing the set times the t, so in our case 25 images. So if you do the cytosolic, if you do the linearization, if you do the membrane profiling and the colocalization in one go, of course, and depending on your resolution of your image, that can take time for the analysis. So keep that in mind. Okay, last but not least, what I want to show you with such kind of 5-dimensional or 4-dimensional images where you have a set or a t dimension as well. I would like to show you what you can do. For instance, you have here at the set position, at the third image, or at the third position in set, a very bad masking result, but the rest is totally okay. Then you can go into this detailed memory masking options, which essentially results in this table where all the options are inside that we have here outside. If you want to use that, you have to enable it. So currently here this is ticked, that's always ticked on by default, but you can untick it. Then we don't use the global membrane masking option anymore. We are using the detailed version. So how it works, we are here at the first, second, third set layer. So we go to the third set position, and now we have here, for instance, the option for dilation. And if we write, instead of false, we should write here true inside, enter, if I would make here a typo or something, say truth, no worries, you get here a message. Also here it's written what you want to write in here. Also in the guidelines there is a place where it is described what do you have to write where, but essentially it follows this. Good. We are activated the dilation option. Now we are using the octagon. We are using the shape 1, 1 in, but only for the image in T1, so time position 1 and set position 3. So let's test it. Now if I move this T, you see the difference here, the dilation worked. Here the dilation is not on, as we told it here. Also here, when we go to set, here the dilations are all switched off. So now here you can specify only for one slice of such a 5-dimensional, 4-dimensional image in detail what you want. If you're satisfied with one specific dilation, maybe we want to dilate everything for every slice and we just want to tweak another parameter, but essentially all the parameters, you don't have to now turn on everything. You can just turn it on here in the global membrane and then transfer the global membrane settings into this table. So if we click here, this false turned into true. I show you just the opposite, that you can see it again. If I untick, so I falsify the dilation option in global, and now I update the dilation, now everything is false. The last thing that I want to show you is how and what we are saving. So first of all, always when you press run and he's done with the calculation, he's also done basically with the basic saving. So what I mean with that is you always get an Excel file and a CSV file. In the Excel file you have the summary, all the summary that you have analyzed, all the objects that you have detected, all the parameters that you have in the object, all the histograms, everything. In the CSV you have the same stuff, just for a global or a free-to-use data format. What you can also save is here in the saving options. So when you have objects detected, you can also save the individual membranes. The cytosolic parts, don't have the cytosolic part here, but we have reanalyzed, and you can save the phasor plot, you can save the color-coded images. What I mean is this one in a TIFF format. You can save all the chooser settings with the metadata as a JSON file. And be aware, you always get this warning, you can also save the analyzed image in an array in the JSON file, which you can simply load into a Python or a MATLAB or essentially everywhere you want to program or you want to do something. But this file will be big because you will have several images in there. But I can show you what happens. And of course you can select here a saving path. I have chosen here the results folder, and when we press run now, so basically this will take now longer because of the save results in JSON. So be aware, only do this on single images, on single stuff, and not on the bulk that you want to analyze, because this will take a very long time. When he's finished, that took nearly 1 minute, you will end up with something like this. In the results you will have the cropped membranes, which you can open in Fiji or ImageJ or other programs that can open these TIFF formats. And you have here this one object that we have detected here in Fiji for all the different formats, all the different objects. Then we have the CSV file, we have the Excel file, that's standard. We have the TIFF of the full image. That's here. And we have this JSON file, which we can essentially open also in an editor or in any program. What it is simply, it is, if you know a data frame, it's kind of a data frame in Python, and here are all the image values inside, all the metadata information, and the settings for the membrane and the analysis are all saved here. So that's everything from my side. Thank you for watching this video. Please like and comment, and yeah, hopefully you have fun with the software.